All right, welcome to homework 3. I want to say a few things about this first problem. It's a complex steam power plant, but we haven't made it to that point in the course yet. We're going to evaluate those, but we should have been talking a little bit about efficiency and improving efficiency. The Rankine cycle is not a reversible cycle, so the more we work on it, the higher the efficiency can get, but it will never surpass the efficiency of a reversible cycle such as the Carnot cycle. So this question, although it gives you some of the details, it doesn't give you enough detail to evaluate fully the efficiency of this steam power plant. That was a little bit by design. What I want you to realize is that given the maximum temperature and the minimum temperature, you could calculate a Carnot efficiency, and any reversible cycle will have that same efficiency. The best that the Rankine cycle could possibly have would be approaching that Carnot efficiency. So the idea here is I want you to make a connection to not 100% being the best possible efficiency, but actually based on reversible cycles. So in this case, if we use efficiency for Carnot, is equal to 1 minus T cold over T hot. Then that represents the efficiency for the Rankine cycle. We'll never surpass that, so it will always be less than the efficiency of the Carnot. So, but this is better than comparing it to an efficiency of 100%. So we know how good is our Rankine power cycle relative to the best we could possibly do being a Carnot. So in this case, it's fairly simple. 1 minus, the only thing, make sure whenever you have a ratio of temperatures, it's going to require that we use absolute temperature scale. So T cold would be the 60 degrees. And T hot 500 degrees plus 273 to express it in absolute temperature, Kelvin in this case, and then we get a maximum possible efficiency where it shows here and the answer is 56.91. So when we're looking at our Rankine cycle and say our efficiency for the Rankine cycle is 50%, you might think, well, that's terrible. We're wasting half of the energy, but when you compare it to the best possible efficiency, it's 56.9, we're doing pretty good. Right, then what would be the maximum possible power? Well, remember that efficiency, both for the Rankine and the Carnot, is the desired output, which in this case is the net power, over the required input, which is our high temperature heat transfer. And we were told the Qin, which is 230,000 kilowatts or kilojoules per second. So we know this high temperature heat transfer and we know the maximum possible efficiency in this case is 56.9%. So we have one equation, one unknown. We can then get, if we use the maximum possible efficiency, and solving for this would give us the maximum possible work. Right? And then the actual work from the Rankine cycle would then necessarily have to be less than that. I hope that helps you a little bit with this problem.